Now, let's look at the need for data structures and algorithms. In general, the software program can be simply expressed as the combined output of data structure and algorithms. When you create a toy house, it's not just a great matter to develop the building plan in our head, and there is no need to worry even if serious problems arise, because they are not highly committed the cost of materials. But if you create a large and luxurious house, it's not possible to build it with just planning in our head alone. Data structures and algorithms are recognized as the most fundamental disciplines in software programming. The data structures and algorithms in the field of enterprise software development uses in various fields and is a discipline which are necessary required for the developers. Like the foundation work required before constructing a high building, in order to operate the software programs efficiently and safely, the algorithms and data structures can be seen as necessarily the basic skeleton of the required program. The biggest goal of an algorithm helps the computer to solve problems and organize how to solve the problems so that other people can come along. Because there are several algorithms to solve the problem, it is very important to use an algorithm right, understanding underlying context. So we should be familiar with the given problem and environment first. For example, because there is an environment that speed is important than resource, and resource important than speed for embedded software development, we should be first aware of this specific environmental context to select the right algorithm. Also, as computers evolve and new or complex problems arise, new algorithms are developed to solve complex problems on its own. Software development cost can be reduced by relieving workload of computer, for example, significant impact to performance. More specific reason to use these algorithms are to ensure efficiency, abstraction, and reusability. In other words, using an algorithm, we can find and leverage the efficient way and classify complex problems into simple problems with our simple aspect. In addition, an algorithm can solve the simple problem efficiently, can also take advantage of a number of other various problem solving. Thus, algorithm has a flash of thought and ideas that can melt and flows from the period of time. But we have little opportunities to take advantage of algorithms in the field due to tight schedules, management orders, and overtime. However, software developers must pursue better performance and higher readability through an algorithm, even if he or she develops the same stuff, and should remember that it is not different from debugging and testing a well. Here, we'll look at how data structure is defined and classified. The program expresses and then processes the expressed data. The representation of the data is a concept that includes the storage of data. Data structures is directly responsible for the storage of this data. In other words, data structures define the integer variables and structures in the broader sense, and the most commonly used data structure is array. We've been often using the word called data. The data can be the note things down miscellaneous information or information noted on books, or things that are stored on computer hard disks can also be said as data. However, among these data, there are data that cannot be roughly created and stored. For example, when you put down the physical or chemical experiment processes on paper, can you list up this information in any order? In this case, you need to record detailed results of each experiment step in chronological order. And what about a list of people attending the company? Because people on the same company have different departments and job titles, in this case, you will need to organize the name of people by job title and department. Like English or Korean dictionary, it should be useless if the words place out of order. It must be sorted in alphabetical order. Users can then conveniently use them. Therefore, the data needs structure. The data structure can be classified into linear, nonlinear, file, and simple data structures. The linear data structure can be classified into lists, stacks, and queues. Tree and graph or nonlinear data structure, sequential file, index files, direct files for file data structure, and simple data structure can be classified into integers, real, character, and string. Among them, let's look at a typical data structure. The most representative list of data structures is a list. This data structure is very easy to add, modify, or delete data. To-do list or experimental steps which were mentioned earlier can be included in list. Next is stack. Stack has the structure which data is piled one on top of another. As it cannot insert new data between the data which are already piled, it can only pile the data at the top. Because if you can't pull out data in the middle, the data at the top can be only deleted. In other words, it's inconvenient to use the data in the middle, so you must remove the data above the data that you want to use. Next is the queue. The queue is the structure which data place in the tunnel with open both ends. Data in the middle, of course, cannot be used now. In general, data is added in the rear, and the front only allows to add or delete data only, but having further developed data structure, we can add, use, delete data at both front and rear. Next is a tree. Tree is linked to each other, and it has hierarchy between data, and therefore it is commonly used data structure for the company organization chart and the family tree. Next is the graph. Graph consists of finite set of nodes, together with a set of unordered pairs of these nodes for an undirected graph or a set of ordered pairs for a directed graph. Unlike the tree, the graph has no hierarchy between data. Accordingly, it can be used a lot for maps, public transport route map, etc. Let's look at the previously discussed linear data structures and the nonlinear data structures such as list, stack, queues, trees, and graph in more detail. Let's look at the linked list, double linked list, circular linked list data structures first. The linked list is a list where connecting the nodes, it refers to as a singly linked list, compared with a doubly linked list to see next. In an illustrative figure, nodes are indicated. This node has a data and a pointer. The data is literally a data field. The pointer can be considered a pointer to the next node. So it can be the linked list interwoven with each other node. The first node in the list is called as the head, and the tail for the last node. Unlike the singly linked list previously discussed, the doubly linked list is able to traverse bidirections. It is a list that connects to the head from the tail and the tail from the head. While a node of a linked list has the only pointer to the next node, a node of doubly linked list has a pointer to the next node as well as a pointer to the previous one. Next, the circular linked list has a cycle structure that is connected to the head and tail. That is, the next node of tail points to the head node. The circular linked list consists of circular singly linked list and circular doubly linked list. Look at the singly linked circular list in the example. You can see that it connects the head and tail from the previous singly linked list. Now, let's look at stack. Let's look at the stack in more detail. Data is inserted and removed only from one end. The next figure shows a stack of full capacity. It looks like a box containing books, and if you want to pull out the data in this structure, you can only get the data at the top in this structure. In the stack, the accumulation of a data is referred to a push, and removal of the data is called a pop. The features of the stack is that the insertion and removal of the data takes place in only one end. Next is a linked list stack. It is a stack based on a linked list. The problem of the stack is that it determines capacity of a stack-like array and data are added. If a stack exceeds the defined capacity, New data can only be inserted once the data on the top of the stack is removed. But this time, linked list stack has the advantage of no restrictions on capacity. Conversely, unlike stack, there is a disadvantage that it takes a long time because insertion and removal into the stack are more complicated. The stack appears in memory structure and have the advantage of postfix expression calculation more simple. This time, let's take a look at the queue data structure. Unlike the stack, that first element added will be removed last. The queue has the structure that first element added will be the first one to be removed. FIFO, first in, first out. For example, assuming that if students are standing in line for lunch, it is considered as the queue that a student exits in turn when he or she gets to receive the lunch. The figure is expressed in simple manner. Here is a point that we need to remember. In the list, we call head in the first of the nodes and tail in the rear node. In the queue, shear elements in the front and as the factor behind the stage. And because the queue has the FIFO structure, removal is made in the head, insertion does in the tail. The queue has a kind of a circular queue and linked queue. Let's take a closer look at it. Now let's look at the circular queue. It is a queue that looks like a circle, not a straight line. Circular queue is designed to solve the problem of queues, which has the linear structure, by making a queue with something circular. The next picture shows the operations associated with the removal of the queue with a linear structure. Initially, the 6 elements in a queue, but A in the front gets out, and all the next elements, B, C, D, E, and F, are moving forward. Whenever the element is removed in the front, other elements behind should come along with element removed. Assume there are 1,000 elements. If the element in the head is removed, elements are further moving forward through 999 times additional computation. That is, the larger the size of the queue and a reduction in performance occurs. As a way to solve this problem, the circular queue has appeared. As you can see in the picture, the circular queue looks like a connection between the start and end, like a doubly linked list. Looking at the next circular queue, you can see that the head is 3, the tail is 10. Note that when the tail of a queue becomes full, if the head and tail are same, we cannot know whether the queue is empty or full. In practice, the tail position is next of the actual tail. And to separate the head and tail, the size of the array have a value that is 1 greater than the actual size of the array by creating dummy element. So, if the head and tail are the same, we can say empty state. If the next node of the tail is a head, we can say full state. Well, this time, let's take a look at the linked queue. Linked queue gets similar to the linked list. Nodes in a linked queue has the address value pointing to the next node. The node is linked from the head to the tail direction. Nevertheless, it doesn't necessarily change the ways of removal operation in the head and insertion operation in the tail. The implementation of the linked queue is quite simple. When insert operation is taken, a new node is added into the next node of the tail node when removal operation position of the head move forward. In other words, when the node in head is removed, simply the position of the head moved to the next node. Insertion also made similarly. Insert the address of the new node to the next node in the tail. Assign a new node to the tail node. For reference, unlike the circular queue, linked queue has the advantage of being flexible because there is no restriction on size. Now, let's look at the tree, which is the representative of a nonlinear data structure tree. The tree is literally the data structure similar to a tree with hierarchical structure. Just like branches and roots in a tree, the tree in the data structure has leaves, roots, and branches. The root is called the root node, the branch is called the branch node, and the leaves called the leaf nodes. The main objective of the tree is a search. So most of the search algorithms use tree data structure. Also, the tree data structure can be used in a wide variety of places, such as decision-making, file systems, search engines, DBMS, routing algorithms, dealing with hierarchical data. If there are differences between other data structures and tree, list, stack, and queue are all linear structures, while tree has a hierarchical structure. From the picture, A is the root, that is the root node, and B, D, E, C, F, G are the branch nodes. I, J, K, L from the branch are the leaf nodes. Having human relationship rather than trees, B and C is the child node of A. Parent node of B and C is A, and the child nodes of B is D and E. Parent node of D and E is B, and the other node as an example. Only root node A doesn't have the parents. And let's take a look at degree, height, and level. Degree is the number of child nodes of a certain node. For example, the degree of the node B is 2. The degree of C node, 2. The degree of the node A is 2. And level is the number in each layer in the tree. Level 1 is A, level 2 is B, and C, and level 3 refers to D, E, F, G. Lastly, the height is the depth of starting from root node of tree to lead node at the end. The depth is referred to the length of the path from the root node to the node refers to. In the above tree case, the depth is 3. That is, A, B, D, I, A, B, E, J, and A, C, F, K all become a tree with depth 3, which start from the root to the leaf. Now let's take a look at the graph, which is the nonlinear data structure. There are differences that while the tree we discussed previously is a kind of directed graph and always has dependency, graphs can be dependency relationship or friends relationship. Take a look at the structure and relevant terms of the graph through the picture. The graph consists of vertex, also known as the nodes, and the edge which connects between vertices. The vertex is where the data is stored, and the edge may also store data in some cases. And the meaning of the degree in the tree is the number of child nodes of certain node. The degrees in the graph indicates the number of edges access to a vertex. For example, the degree of the vertex 3 is 3. The degree of vertex 5 becomes 2. This time, between vertices that can pass through edge once is approach or adjacent, that is, 1 and 4 nodes are approaching, but it means that 4 and 5 nodes are not adjacent. In addition, we express approach or intersect if two edges access to the same vertex. For example, it can be said approach where two edges access to the same node 5. Here, there are names in some special graphs. As we have seen the graphs so far, we call them undirected graph as there is no direction. In other words, if assuming the edge is a road and vertex is an area, it may become back and forth from area 1 to area 4. On the other hand, the graph with direction on the screen is called the directed graph. That is, it can go from number 5 to number 3, but can't come from number 3 to number 5. Therefore, a directed graph counts separately the outgoing edge and incoming edge. Finally, the complete graph indicates a graph with all vertices adjacent. That is, there are n vertices, and a graph that has all vertices with n-1 edge. The sample picture of the screen represents the undirected graph as well as the complete graph, having 5 vertices and 4 degrees of all vertices. Now, how do we think of a good algorithm? We always have a problem in the field and always think how to solve the problem with a solution, that is, an algorithm. Software developers think various algorithms to solve the problem, and would have to choose the best algorithm and what factors are considered when an algorithm is selected. We will tell you to explain the Google case, for example. The following is a famous known problem that was used to test the applicants on Google. We will explain how to solve the problem given while we are solving it. Firstly, solve it bravely, believing computer power to calculate a loop from 1 to n in a simple way. Perhaps it requires a number of hours to run, but also stop the run. It is the use of a simple algorithm. It is the code to check whether 1 is included for any number smaller than the input number. It can be seen that the amount of calculation is continuously increasing to 1 plus 2 plus 3 plus 4 plus 5. This method is not a very smart approach. Now we will solve the problem more smartly. The codes already calculated are just skip the codes above can be solved, but takes very inefficient way. It is also known as ad-hoc coding. In the field, it brings many benefits to the extent that some minor changes to the above codes. It uses a method that adds the accumulating number of 1 previously found. Since the values are accumulated, you do not need to repeatedly calculate what was previously calculated. If you test the following codes, you'll see that the answer is found within 0.1 seconds. The time of execution results is 0.03 seconds. You can see that the answer is extracted in results in a very short time. Number 3 is that find a pattern. You search and define the commonly used algorithms. Complex phenomenon also has the certain rules. Once this rule is found, it becomes possible to improve problem-solving skills with a better awareness of the phenomenon. Firstly, let's have a look at what kinds of patterns they have. If first digit is 1, number of digits multiplied by 10 plus 1. If the first digit is not 1, 10 square of number of digits minus 1 and plus n divided by 10 and multiply number of digits minus 1. Finally, a certain pattern comes out. We do a recursive call to this pattern. However, this is not yet finished. In each recursive call, which the first digit is not 1 has nothing to do with this, but in the case of which first digit is 1, for which all values are increased, 1 additionally occurs as much as number of digits. Therefore, if the first digit is 1, the following formula will be applied. The result of the applying above formula is added by the size of the current position. For example, if 1100, the following formula makes it to 422. If it is 1120, it is 444. We can set up an assumption here, from which the first number is 1. The number including the largest number is that all but the first are 9. Therefore, without a need for validating all, the smallest number starting with 1 and a large number is greater than a given value are validated and then calculated. Therefore, after applying the above formula 5 times, the number we want is confirmed in position between 100,000 and 199,999. This approach does not seem to be very efficient compared to the second method. Even if the actual time tests is performed, it is not going to be faster than the second method, and this formula is too complicated. In order to create the perfect formula, there will be quite a lot of testing. But while these shortcomings, with this case, it has the advantage of general usage, reuse of this algorithm in other places. Code using this formula is able to be solved the common problems, that is, calculate the value of n more efficiently. In the case of the second approach, it should be recursive by n, but this approach obtains the value by the recursive calls with number of digits. If the problem is to get the values of tens of millions, tens of thousands of random function n, this approach will be operated more efficiently. The fourth is find the key. Another way to easily solve the problem is to narrow the range to find one of the core key. This is very useful when particularly solving an arithmetic problem. Let's consider the following problem. If this problem is greatly enlarged, the answer to this problem doesn't come in clearly visible. The key is the y plus n equals y part. In this equation, if y is to come as the result, you can find out the n should be 0. If we are aware of this, it turns out that it can easily solve the problem. Now let's take a look at the search algorithm. The typical search algorithms are sequential search and binary search tree. First, the sequential search is the algorithm to find the desired data by comparing the order from the beginning to the end of the data array. While such sequential search has the advantage of being simple because of not necessary to manipulate the data separately, it does have the disadvantage of being inefficient. It is also called a linear search because it performs a one-way search. Linear search is simple to implement because of its simplicity. In an unsorted data array, it takes an average of n plus 1 divided by 2 comparisons. The time complexity is big O, n. In the worst case, it ends the program with n times comparison. Next, a binary search is reduced by half when a comparison is done in assumed sorted array, unlike a linear search. Let's look at how fast these binary search is, for example. Assuming that among the 7 billion people search specific information, while the sequential search is 35 billion times comparison on average, a binary search is very fast because it is able to find the data maximum 33 times comparison. Now let's look at how to go through the process when a binary search algorithm is applied in an ordered array, as shown in the picture. Assuming that search the data 8, the first step is set of data. Select the middle element 7. Then the second is to compare the value of the middle element with the searching element. If value you are looking for is similar than the value of the middle element, then selecting a middle element again on the left side of the middle element, but if searching the element value is greater than the value of the middle element, then the middle element are selected in the right. For example, there is no need to compare in the left because the searching element 8 is greater than middle element 7. Select the middle element again in the right of the middle element. Now the middle element value becomes 9. It will again be comparing the middle element with the searching value. Because the searching value 8 is smaller than the middle element 9, select the middle value in the left side again. The remaining value 8 becomes the middle value, and the search has been finished while it is consistent with the data we are looking for. So let's have a look at the performance of this binary search algorithm. Every time the comparison is made once, the range is reduced by half. Suppose the size of the data set is n, and the number of iterations is k. Then a formula is created, such as shown on the screen. This shows the formula which expresses how many times the size of n data sets divided by 2. It finally becomes k equals log squared n. For example, if the size of the data set is 5 million, the data can be found through maximum 22 times. If it's 10 million, the data will be found with up to 23 times searching. Next, the binary tree applied with a binary search has 4 properties. It doesn't have the child nodes at all. There is only one left or one right child node, or having both left and right child nodes. Therefore, a binary search tree has the maximum number of child nodes 2. Let's look at the rules of the binary search tree in the picture this time. The most key is that the left child node is smaller than the parent node, and the right child node is greater than the parent node. If you want to find the data 14, it is greater than the root node 10, it will compare with the right child node 17. Because the data 14 we want to find is less than the data 17, look at the left child node. When those are matched by comparing the value you want to find, the search is ended. In this case, there is a data you are looking for in the tree. What happens if you want to find not in the tree? For example, let's suppose to find 16, which is not in the tree. Because the searching value is greater than the root node 10, the right subtree is visited. The left child node is revisited because the right child node is 17, and it's greater than the value you want to find. A left child node, 14, does not have any child nodes. Even if it revisits the child node, 21 again, it has null value. This binary search tree shows the worst efficiency in skewed binary tree which has one side skewed. The time complexity of skewed binary search is order of n, and in case of which it is similar to the complete binary tree to demonstrate order of log n. The form of a binary search tree is recommended to organize similarly to the complete binary tree.